Good evening, and welcome back to The Resting Researcher. Tonight, we're exploring something almost impossible to grasp. Not a place, but a scale. A way of measuring time so vast that human history becomes a single grain of sand on an endless beach. We're talking about deep time, geological time, the 4.6 billion years since Earth formed, compressed into a story we can begin to understand. Before we begin, I'd love to know where you're listening from tonight. And if these gentle explorations of science help you wind down, please consider subscribing and liking this video. It helps others discover this calm approach to learning. I hope this journey through time is fascinating enough to hold your curiosity, yet soothing enough to guide you peacefully toward rest. And if you stay awake through all of it, at least you'll have a new perspective on just how ancient our planet truly is. So, settle in, get comfortable, and let's travel backward through billions of years, watching continents form and vanish, mountains rise and erode, and life emerge from the simplest chemistry to the complexity we see today. 4.5 billion years. It's easy to say, but almost impossible to truly comprehend. Human lifespans are measured in decades, civilizations in centuries or millennia. But Earth has existed for thousands of millennia, millions of millennia. To help make sense of this, geologists have developed various metaphors. One of the most helpful is the calendar year analogy. Imagine Earth's entire history compressed into a single year. January 1st is the formation of the planet. December 31st, at midnight, is right now. In this calendar, Earth forms on New Year's Day. For the first few months, the planet is molten, bombarded by asteroids and comets, gradually cooling. The first simple life, bacteria, appears around late February or early March. For most of the year, that's all there is. Single-celled organisms in the oceans. Complex multicellular life doesn't appear until November. The first animals with shells show up in mid-November. Plants colonize land in late November. Dinosaurs appear around December 13th. They dominate for about a week and a half, then vanish on December 26th when an asteroid strikes. The first recognizable human ancestors appear on December 31st at about 11:30 p.m. Agriculture begins at 11:59 p.m. The pyramids are built 11 seconds before midnight. The entire span of recorded human history fits into the final minute of the year. This perspective helps illustrate just how young humanity is compared to Earth itself. We've been here for less than a blink in geological terms, but even this calendar metaphor doesn't quite capture the immensity of deep time, because each day in this calendar represents over 12 million years. Each hour represents about 500,000 years. Events that seem ancient to us, the fall of Rome, the building of Stonehenge, the last ice age, all occur within the final few seconds of December 31st. Geologists divide Earth's history into formal units. The largest are eons, which last hundreds of millions to billions of years. Eons are divided into eras, eras into periods, periods into epochs, and epochs into ages. The names of these divisions, Cambrian, Jurassic, Pleistocene, come from the places where rocks from those times were first studied, or from characteristics of the rocks themselves. The current eon, the Phanerozoic, began about 540 million years ago, when complex life became abundant. Before that was the Proterozoic eon, lasting from 2.5 billion to 540 million years ago. Before that, the Archean eon, from 4 billion to 2.5 billion years ago. And the earliest time, the Hadean eon, from Earth's formation to about 4 billion years ago. Each of these eons saw dramatic changes. The Hadean was a time of intense heat and bombardment. The Archean saw the first continents forming and the first life appearing. The Proterozoic witnessed the oxygenation of the atmosphere and the evolution of complex cells. And the Phanerozoic, our current eon, is characterized by abundant fossils, visible life preserved in stone. Deep time is recorded in rocks. Each layer of sediment represents a slice of time. A sandstone layer might record of an ancient beach, a limestone layer, a shallow sea, a coal seam, a swamp that existed millions of years ago. By studying these layers, geologists reconstruct Earth's history. They determine which rocks are older and which are younger, based on a simple principle. In undisturbed sequences, deeper layers are older. This is called the law of superposition, one of the foundational principles of geology. It seems obvious now, but it wasn't always understood. For much of human history, people believed Earth was only a few thousand years old. It was only in the 18th and 19th centuries that scientists began to recognize the immense age of the planet. They noticed that sedimentary rocks were often thousands of meters thick, representing countless layers of deposition. If each layer took years or decades to form, the total time required was staggering. James Hutton, a Scottish geologist in the late 1700s, proposed that Earth was far older than anyone had imagined. He coined a phrase that captures the essence of deep time: no vestige of a beginning, no prospect of an end. Hutton understood that the processes shaping Earth, erosion, sedimentation, mountain building, operated slowly but continuously. Given enough time, they could transform entire landscapes. Later, in the 20th century, scientists developed radiometric dating, a method of determining the age of rocks using radioactive isotopes. This provided actual numbers, ages, in millions and billions of years. Radiometric dating works by measuring the decay of unstable isotopes. Uranium slowly decays into lead. Potassium decays into argon. The rate of decay is constant and predictable, like a ticking clock embedded in the rock. By measuring the ratio of parent isotope to daughter product, scientists can calculate how long ago the rock formed. This technique has allowed us to date Earth itself, along with meteorites and moon rocks, to about 4.54 billion years. That number, 4.54 billion, is our best estimate for the age of the planet. It's not just a guess. It's based on measurements from dozens of samples, all pointing to the same ancient origin. As we pause here, try to picture the sheer span of time we're discussing. If you extended your arms wide, fingertip to fingertip, representing all of Earth's history, the entire existence of humanity would fit within the thickness of the fingernail on one hand. All of recorded history, every empire, every invention, every story ever told, would vanish with a single stroke of a nail file. That's deep time. And understanding it changes how you see the world. Let's journey back to the beginning. Not to the Big Bang or the formation of the solar system, but to the moment Earth itself coalesced from the swirling disk of dust and gas around the young sun. About 4.6 billion years ago, gravity pulled together countless small bodies, planetesimals, made of rock and ice. They collided and merged, each impact adding mass and generating heat. The early Earth was a molten ball. The surface was covered in magma oceans, glowing red and orange, radiating heat into space. There was no solid crust yet, no water, no atmosphere beyond the gases released by volcanic eruptions and asteroid impacts. This earliest time is called the Hadean Eon, named after Hades, the Greek underworld. It was a hellish place, at least by the standards of life as we know it. For the first few 100 million years, Earth was continuously bombarded by leftover debris from the solar system's formation. Some of these impacts were enormous. One, occurring about 4.5 billion years ago, involved a Mars-sized body called Theia colliding with Earth. The impact was so violent that it vaporized much of both bodies. The debris ejected into orbit eventually coalesced to form the Moon. This is the leading theory for the Moon's origin, and it explains why the Moon's composition is similar to Earth's outer layers. After the moon-forming impact, Earth had to cool and solidify all over again. Gradually, over tens of millions of years, the surface cooled enough for a solid crust to form. The oldest minerals we've found, tiny zircon crystals from Western Australia, date to about 4.4 billion years ago. These zircons are remarkable. They're barely visible, smaller than a grain of sand, but they've survived for almost the entire age of the Earth, and locked within their crystal structure are clues about the conditions when they formed. Analysis of these zircons suggests that liquid water may have existed on Earth's surface as early as 4.3 billion years ago. This is astonishing because it means oceans formed much sooner than previously thought, within just a few 100 million years of the planet's formation. Where did the water come from? That's still debated. Some likely came from within Earth, released by volcanic activity as water vapor. Some may have been delivered by comets and asteroids, icy bodies from the outer solar system that struck Earth during the late heavy bombardment. Whenever and however it arrived, water changed everything. It allowed weathering and erosion to begin. It created an environment where chemistry could become more complex, and eventually, it provided the medium where life would emerge. By about 4 billion years ago, Earth had oceans, a thin crust, and volcanic islands. The atmosphere was still very different from today's, mostly nitrogen, carbon dioxide, and water vapor, with no free oxygen. But it was stable enough for more complex processes to begin. Somewhere in those early oceans, perhaps near hydrothermal vents, on the seafloor, or in shallow tidal pools, simple organic molecules began to form. Amino acids, nucleotides, lipids, the building blocks of life. We don't know exactly how life began. It's one of science's great unsolved mysteries, but we know it happened early, because the oldest fossils, traces of bacteria-like cells, date to about 3.5 billion years ago. These early organisms were simple, single cells with no nucleus. They likely fed on chemicals in the environment, not sunlight. But they could reproduce, passing on information from one generation to the next. And once life existed, evolution could begin. Mutations introduced variations. Natural selection favored traits that improved survival. Over millions of generations, life diversified. Around 2.5 to 3 billion years ago, some bacteria evolved the ability to photosynthesize, using sunlight to convert carbon dioxide and water into sugar and oxygen. These cyanobacteria were the first organisms to release oxygen as a waste product. At first, the oxygen didn't accumulate in the atmosphere. It reacted with iron dissolved in the oceans, forming rust that settled to the seafloor. These ancient rust deposits, called banded iron formations, are some of the oldest and richest iron ore deposits on Earth. But eventually, around 2.4 billion years ago, the oceans became saturated with oxygen. There was no more dissolved iron to react with. And so, for the first time, free oxygen began to accumulate in the atmosphere. This event is called the Great Oxidation Event. It was one of the most significant changes in Earth's history. Oxygen is toxic to many of the organisms that existed at the time, and mass extinctions likely occurred. But oxygen also opened up new possibilities. With oxygen in the atmosphere, new types of metabolism became possible. Aerobic respiration, which uses oxygen to break down sugars, is far more efficient than anaerobic processes. Organisms that could use oxygen had a huge advantage. Over the next billion years, life slowly diversified. cells became more complex, developing nuclei and organelles. This is the origin of eukaryotic cells, the type of cell that makes up plants, animals, fungi, and many single-celled organisms today. For a long time, though, life remained microscopic. The oceans were full of bacteria and single-celled eukaryotes, but there were no animals, no plants, nothing visible to the naked eye. This period, from about 2.5 billion to 540 million years ago, is sometimes called the boring billion, because it seemed like not much was happening. But beneath the surface, profound changes were underway. Cells were learning to cooperate, forming colonies, experimenting with multicellularity. And then, relatively suddenly, everything changed. About 540 million years ago, something remarkable happened. Within a geologically brief period, perhaps just 20 to 25 million years, nearly all the major groups of animals appeared in the fossil record. This event is called the Cambrian explosion, and it marks the beginning of the Phanerozoic eon, the eon of visible life. Before the Cambrian, fossils are rare and mostly microscopic. After the Cambrian, the rocks are full of them. Trilobites, brachiopods, early mollusks, primitive arthropods all appear suddenly. Why did this happen? No one knows for certain, but several factors likely contributed. Oxygen levels in the atmosphere and oceans had risen to levels that could support larger, more active organisms. Predators evolved, creating an evolutionary arms race that drove diversification. And changes in ocean chemistry may have made it easier for animals to build shells and skeletons. The Cambrian seas were strange by modern standards. Trilobites, distant relatives of insects and crustaceans, crawled across the seafloor. Anomalocaris, a giant predator over half a meter long, hunted with grasping appendages and a circular mouth. Hallucigenia, a tiny creature covered in spines, looked like something from a nightmare. Many of these early animals belonged to groups that no longer exist. They were evolutionary experiments, some of which succeeded and gave rise to modern groups, and some of which left no descendants. Life remained in the oceans for now. The land was still barren, a rocky desert devoid of plants or animals. But in the water, ecosystems were becoming complex. Food webs formed. Predators and prey, scavengers and filter feeders. By the Ordovician period, about 485 million years ago, life had diversified further. Corals appeared, building the first reefs. Fish evolved, the first vertebrates, ancestors of all animals with backbones. Then, around 450 million years ago, plants began to colonize land. The first were simple moss-like organisms that hugged the ground near water. But they were pioneers, and they transformed the landscape. Plants stabilized soil. They added organic matter. They created habitats for the first land animals, which followed soon after. Millipedes, early arachnids, wingless insects, all of them small, but all of them adapting to a world without water. By the Devonian period, about 400 million years ago, forests had appeared. Not forests as we know them, but groves of primitive plants like Archaeopteris, a tree-like organism with fern-like leaves. And in the water, fish were diversifying. Some evolved jaws, some grew armor, and some, in a critical step, developed lungs and fleshy fins that could support weight. These lobe-finned fish were the ancestors of all tetrapods, four-limbed vertebrates. Around 375 million years ago, some of them began venturing onto land. Tiktaalik, a famous transitional fossil, shows features of both fish and early amphibians. It had gills but also lungs, fins, but also a neck and ribs that could support its body out of water. This was the beginning of the vertebrate conquest of land. Over the next 100 million years, Amphibians diversified. Some remained tied to water, laying eggs in ponds, but others evolved into reptiles, which developed eggs with tough shells that could survive on dry land. Reptiles no longer needed water to reproduce. They could live entirely on land, in deserts, on mountains, anywhere. This opened up enormous new territory. By the Carboniferous period, about 350 million years ago, the land was covered in dense swamp forests. Giant ferns and early relatives of conifers grew to enormous sizes. The climate was warm and humid, and the oxygen levels were higher than they've ever been, about 35% compared to today's 21%. This allowed insects to grow to enormous sizes, dragonflies with wingspans of over half a meter, millipedes as long as a person, scorpions the size of house cats. These forests eventually became coal. When the plants died, they fell into the swamps and were buried by sediment. Over millions of years, heat and pressure turned them into coal seams that we mine today. The Carboniferous gets its name from this carbon-rich legacy. Then came the Permian period, about 300 to 250 million years ago. Reptiles continued to diversify. Some lineages led to mammals, others to the ancestors of dinosaurs. The supercontinent Pangaea formed, bringing all of Earth's landmasses together into one giant continent. But the Permian ended in catastrophe. About 252 million years ago, the worst mass extinction in Earth's history occurred. The Permian Triassic extinction, sometimes called the Great Dying. Over 90% of marine species went extinct. About 70% of land species vanished. The exact cause is debated, but massive volcanic eruptions in Siberia, releasing huge amounts of carbon dioxide and sulfur, likely triggered climate change and ocean acidification. Life came perilously close to being wiped out entirely, but it survived. And in the aftermath, new groups rose to dominance. The Triassic period, beginning 250 million years ago, saw the recovery of ecosystems, and from the survivors emerged a group that would dominate the planet for the next 180 million years: the dinosaurs. Dinosaurs first appeared in the late Triassic, around 230 million years ago. They were initially small, overshadowed by other reptiles. But after another mass extinction, at the end of the Triassic, they rapidly diversified. The Jurassic period, from 200 to 145 million years ago, is when dinosaurs truly came into their own. Giant sauropods like Brachiosaurus and Diplodocus grazed on treetops. Theropods like Allosaurus hunted in packs. Stegosaurus defended itself with spiked tails. The climate was warm and humid. Sea levels were high. Shallow seas covered much of the continents. Forests of conifers and ferns stretched across the land. Birds evolved during this time, descended from small feathered theropods. Archaeopteryx, one of the earliest known birds, had features of both dinosaurs and modern birds. Teeth and a long bony tail, but also feathers and wings. The Cretaceous period, from 145 to 66 million years ago, was the final chapter of the dinosaur age. It saw the evolution of some of the most iconic dinosaurs: Tyrannosaurus rex, Triceratops, Velociraptor. Flowering plants appeared during the Cretaceous, revolutionizing ecosystems. Bees and butterflies evolved to pollinate them. Mammals remained small and mostly nocturnal, living in the shadows of the dinosaurs. Then, 66 million years ago, the age of dinosaurs ended abruptly. An asteroid about 10 kilometers across struck the Yucatan Peninsula in what is now Mexico. The impact released energy equivalent to billions of nuclear bombs. It created a crater 150 kilometers wide. The immediate effects were devastating. Wildfires swept across continents. A cloud of dust and debris blocked out the sun for months or years. Temperatures plummeted, photosynthesis stopped, ecosystems collapsed. About 75% of all species went extinct, including all non-avian dinosaurs. The only dinosaurs that survived were birds. But the extinction also created opportunities. Mammals, which had been small and marginal, suddenly had access to ecological niches previously dominated by dinosaurs. They diversified rapidly. The Cenozoic era, beginning 66 million years ago and continuing to the present, is sometimes called the Age of Mammals. Mammals evolved into enormous variety. Some took to the seas, becoming whales and dolphins. Others took to the air as bats, and some remained on land, growing large and diverse. Primates, the group that includes monkeys, apes, and humans, appeared early in the Cenozoic. For most of their history, they were arboreal, living in trees and tropical forests. Then, a few million years ago, some primates in Africa began to walk upright. They came down from the trees and onto the savanna. Their brains grew larger. They developed tools, language, and culture. By 300,000 years ago, Homo sapiens, modern humans, had appeared. We spread out of Africa, colonizing every continent except Antarctica. We developed agriculture, cities, writing, and technology. And now here we are, a species that has existed for less than 0.01% of Earth's history, trying to comprehend the vast sweep of time that came before us. As we come to the end of our journey through deep time, let's reflect on what we've seen. Earth has existed for 4.6 billion years. For most of that time it was lifeless. Then, for billions of years more, life was microscopic. Complex life, plants and animals, has only existed for about 2% of Earth's history. Humans have been here for a vanishingly small fraction of that time. All of human civilization, from the first farms to the present day, fits into the last 0.022% of Earth's history. This perspective is humbling. It reminds us that we are recent arrivals on an ancient planet. The mountains, the oceans, the rocks beneath our feet have stories far older than any human story. But it's also awe-inspiring. We are part of a process that stretches back billions of years. The atoms in your body were forged in stars. The oxygen you breathe was released by ancient bacteria. The land you stand on was once the seafloor or the peak of a long-eroded mountain. Deep time connects us to everything that came before and everything that will come after. Thank you for joining me on this journey through Earth's ancient history. I hope it gave you a new appreciation for the age of our planet and the vastness of geological time. As you drift towards sleep tonight, picture the long, patient unfolding of history. Mountains rising and falling, continents drifting, life emerging, evolving, diversifying. All of it happening on timescales far beyond human comprehension. And rest easy, knowing that Earth will continue, turning, changing, renewing itself, long after we are gone. Sleep well,